Welcome to the 17th class meeting of the Introduction to DSP. As I told you, the chapter 4 is not only about sampling of a continuous time signal, but also it's related to the sampling of discrete time signals. However, I told you there is a misnomer that confuses us a lot. So I'm going to tell you about that first. So here, as the review shows, we did this one in the first part of the chapter 4, where you had a continuous time signal, and there could be a single stage representation, but let's do the two-stage representation. Here goes the so-called sampling function, which is an impulse train. And then you have a continuous time sampled signal, x s of t. And then here comes a strange box called impulse train to dt signal. So you have your output discrete time signal. And this process of having a discrete time sequence, the nth term, as the evaluation of the continuous time signal at an integer n times t, let me use ts, okay, sampling interval. So this is called sampling, got it? So when you just say sampling, implying sampling of a continuous time signal, this is the process. What was the opposite process? It was something like this. Suppose you have a discrete time signal, then what do? You convert it to a continuous time impulse train. So here, dt signal to ct impulse train, actually modulated impulse train. So you have here, let me see, y c of, is it y s y c? I'm not sure. And you have your nth term multiplied by delta of t minus n times t sub I. Here, the lower part is not necessarily the inverse operation of the upper part. So I use the different interpolation or conversion period. And here goes your interpolation filter or interpolation function. So you have here a continuous time signal, which can be simply written as yn h of t minus n ti. This second part is called interpolation. And here you have an interpolation filter. If we follow exactly the same idea, when we have discrete time signal in, discrete time signal out, similar operations, we'd better call this as sampling and this called interpolation. However, people didn't do it. That's the confusing part. So here you have a discrete time signal and you downsample by m. What does that mean? Here you have, let me use x d of m, which is simply x evaluated some capital M times m. So what you do is basically remove capital M minus 1 samples at every m length m section of the original signal. And this is very similar to that one in the sense that here you have uncountably infinite pair of T and XC where you keep some countably infinite number of pairs. And here you have countably infinite number of pairs, and still you keep countably but much smaller, one mth of the pairs. Got it? So in the sense that this could be called sampling. However, the signal processing guys call it downsampling. Got it? Then when we have downsampling, we may have some preceding filter. In that case, we call this process as decimation. Got it? And when we have a discrete time signal and we have upsampling by a factor of L, what does that mean? You have output let me see. L equals L. Let me use. So when we divide lowercase l by capital L and its remainder is 0, then we have what? The original signal, x. Got it? And otherwise, we have zeros. So this basically inserts capital L minus 1 zeros between two consecutive samples of the input. And this is called upsampling. And sometimes we have upsampler followed by interpolation filter. And this is, of course, called interpolation. Got it? And in order to remember clearly, I kind of gave you a mnemonic to memorize this one, right? So you will never forget. Got it? So they wanted to have these terminologies, upsampling, downsampling, and upsampling. So as you see, this is a little bit different. Of course, this part, the interpolation, is very similar to this interpolation, right? You have some process to do upsampling and you have a filter. And here you have DT to CT impulse train converter and interpolation filter. Got it? So the first thing you need to do is to remember without confusion what is sampling over continuous time signal, what is an interpolation of a discrete time signal to have a continuous time signal, and what is downsampling, what is an upsampling, and what is a decimation, and what is interpolation of DT signal to obtain a DT signal. Got it? So in the, of course, time domain. So your story is not yet done, and you need to analyze it in the frequency domain. And that's what you see. And interestingly, these two operations, sorry, not these two. these two operations have a very interesting filter bank implementation method. The textbook says efficient method, but anyway, that efficient method use a filter bank for each one. And for the downsampling, we've covered it in detail. And for upsampling, I just scratched the surface very fast, so let me repeat. By the way, the textbook has very confusing notation. So I tried to change the time index to L for the kind of upsampled version of the signal. However, I later found that the textbook uses the lowercase l in other use, so it's very confusing. But anyway, so this is what you've seen, right? Precisely speaking, this is not upsampling, but interpolation. And this part is upsampling, precisely speaking. So in the time domain, the thing you need to get is this part, conversion from this line to that line. And it's very interesting because this reveals that upsampling, zero insertion, is a very special case of interpolation where the impulse response of the interpolation filter is the delta function, which means this one has delta of L, which means that you don't need that, right? Because if the LTI system has impulse response delta of t, it's an identity system. So it reduces to that one, right? So you need to do it yourself, as I told you. Otherwise, it's more and more confusing as we proceed to cover multi-rate signal processing today. So this is necessary. You just don't fold your arm and just use eyeball. Don't do that, okay? The interesting part of the systems research in electrical engineering is that your capability is strictly proportional to the used lead in your lead pencil. Got it? 샤프심의 질량과 실력은 비례한다 이런 말이 있죠. 사용한 샤프심의 질량과 볼펜으로 하지 마세요. Okay, so here goes the frequency domain representation, and it's not that difficult. Whenever you want to have frequency domain understanding, just compute the discrete time Fourier transform. So this is the expanded version where this is marked as expanded version, and this is called interpolated version. So x sub e of L, got it? Zero insertion version is after you have this equivalent notation. It's very simple. Summation, term, and e to the negative j omega L. I change it to L. And then you can easily show that it's really a scaled version. But since in the time domain it is expanded, in the frequency domain it is compressed. Right? So it's compressed by L in the frequency domain. And we've seen here, right? So this one is compressed by, in this case, 2, because this example has L equals 2. Right? So this is the x sub e over L's DTFT. If you put an interpolation filter like this, then you can remove these things. Right? So upsampling is an interpolation, as I have told you. Remember this, these two Venn diagrams. And here goes very special interpolation filters, impulse response. The first one is that when L equals 5, you have this linear interpolation filter having 1, 2, 3, 4, 5, -1, -2, 3, 4, 5. So when you shift this impulse response by 5, then this peak is located at 0. Got it? In this way, you can do something like this. Suppose your signal is causal and have these samples. And now, expanded version of it by 5 would be what? This is 0, and this is now 5, that is 10, and you have 1, 2, 3, 4, 6, 7, 8, 9. Now, suppose you have that interpolation filter, then what do? Basically, you convert this single sample to what? Something like this. And then for this sample, of course, you have these interpolation procedures. So as I told you, this value from the original sequence is not altered at the output of the linear interpolator. So you have this one, and that one still there. And because as you learned in high school, actually it was very confusing, but as you learned in your high school math, if you sum up these two curves, then what happens? You have a linear function, right? So within this interval, this is linear, that is linear, sum is linear. And you have this value, you have that value. So actually, you really linearly interpolate your signal. Got it? But even after the interpolation, you have the same values here. Got it? Of course, this is not always occurring. If you have some interpolation filter that has non-zero values, for example, for capital L, then you have some distortion. And that is, if you have taken communications course, is very similar to so-called the intersymbol interference. Got it? Anyway, so you have this filter, and this filter has the frequency Fourier transform, which is similar to sinc square. But as you see, what was this one? What was this one? It's a Dirichlet kernel. Got it? Of course, our definition and the definition from Wikipedia is a little bit different. But anyway, so it looks like a sinc function, but it's periodic. So you have some in the omega domain, you have this one exactly copied and shifted by 2 pi. So you have this copy repeated again and again, something like that. Anyway, so here goes the efficient implementation of interpolator. And that also starts from this representation of the expanded version of the signal. So this is so important. Right? After you convolving, you have that one. And when L equals 2, you have something like this. right? And here, for L equals 2n and L equals 2n plus 1, you have something interesting. So as you see, the interpolated signals at the even time instant is given like this. And what you want to do is that you factor these two out so that you have h of 2n as your new impulse response named h sub 0. 0 is even number, so 0. So you have n, n, n. Ready? By the way, of course, the output is some discrete time signal with time index n. And if you change n, then this is a sign. Ready? So let's say the output is y of n, y0n, then that is defined this way. And this is y1 of n, which is defined this way, in a similar way. Got it? So it's like whenever you have something to be generalized, start from 1. Usually you don't need to do anything. Then try 2. This textbook exactly does that. For L equals 2, you derive without that much difficulty. And then next is general capital L. So in Korean, 하나, 둘, 많다. Then you have, voila, this one. Not this one. This is L equals 2 case. And here, by the way, this part is called commutator. So commutator takes this value, that value, and that value, and that value by alternating the switch. And here is your filter bank and single input. So after generalization, you have a filter bank with a capital L filters whose impulse responses are what? Sampled version of the interpolation filter with different offset. Got it? So you have different offset. Got it? Let me use L. Same interpolation filter sampled with different offset with interval capital L. Got it? So up to this point, you still have low rate, low rate, low rate, and suddenly this commutator sweeps very quickly per each n time index, L times, and then it generates high rate signal. So this is up converter in the special case, and it's a interpolator. Got it? And this part is not that difficult, so you do it yourself. So what you need to do is that the interpolator can be written in this form and also in that form. Got it? And you must be capable of handling both of the representations. An interesting thing is, interesting interpretation of this filter bank approach can be also understood in the frequency domain. So let's do it. So let's call h sub L of n as the Lth interpolation filter, sampled from the original interpolation filter. And what we do is that we compute h sub L in terms of capital H. Got it? So this is the DTFT of h of L. And this is DTFT of h sub L. I really hate of n. Yeah, as I told you, the authors use L again, so I'm kind of Anyway, so after you somehow manipulate this one, you have something interesting. Here, you have L and you have, just a second, what is K? Yeah, you have L here, you have L here. So after you take the absolute value, if this one has the magnitude like the ideal low-pass filter with cutoff pi over L, interestingly, am I doing correct? Yeah, I believe so. So first, you need to expand that one in this way, right? Because if you replace omega with omega over L, then actually you expand in the frequency domain. And you have this one, as you've just seen, and has very interesting thing. If you have the original interpolation filter, the ideal low-pass filter, then you have else filter in the filter bank has linear phase. So this is called the, let me skip it, polyphase interpolation. So your zeroth filter has frequency response 1 for all omega. First one has linear phase shift. Second one has also linear phase shift. And what's the meaning of linear phase shift, by the way? Delay in the time domain, as you learned in signal gen systems. And actually, if you have having an ideal low-pass filter means that your interpolation filter is delta function. And delta function delayed gives you linear phase shift. Of course, in general, your filter is not an ideal low-pass filter, ideal delta function. So you have something different, but after you factor the common factor out, you still have a linear phase shift. Got it? And linear phase shift is due to this one. See that? You compare these two. What's the difference? You have delay. Got it? So you have a linear phase shift. You read this part and can easily understand. Got it? Okay. Here goes the today's topic. And today's topic is the multi-rate signal processing. And multi-rate signal processing is a kind of discrete time signal processing where you not only have downsampler, but also has upsampler, or vice versa. And sometimes these down and upsamplers, sometimes in the form of decimator and interpolator, is used to do some kind of processing, not necessarily changing the sampling rate of original continuous time signal to some other rate. So there are two interpretations. First is that you have a continuous time signal sampled at 1 over Ts. And we want XCT resampled at some integer, some rational multiple of the sampling rate. Got it? As I told you, it shouldn't be square root of 2 or 3, something like that. 1 over 2, 2/3, 7 to 8, 7 to 8, something like that. Second one is purely you have xn somehow upsampled and processed and downsampled, or downsampled, processed, upsampled. So this multi-rate signal processing sometimes is related to the sampling rate change. However, it's not always covering that topic only. Anyway, as this block diagram clearly shows, and here you have L times the upsampling by a factor of L, and you have interpolation filter, and you have kind of pre-filter for the decimation, and you have downsampler. Got it? And as you see easily, these two are LTI systems. And as you learned in signal gen systems and the review of this course, you can just simply replace these two signals convolved as a single signal, which is used the impulse response of this field. Got it? So you need to change the kind of DTFT figure by compressing and expanding in the frequency domain and aligning a lot. So let's see. The first thing is changing the sampling rate to a rational multiple of the original sampling rate. And of course, you can, as I told you, some simple way is that you have a sampler. So you have a discrete time signal, and here you convert it back to some continuous time signal and resample for any arbitrary sampling period. But as I told you, if the sampling rate, the desired sampling rate is an integer, the rational multiple of the original sampling rate, then you don't need to do this CT conversion of DT signal. You don't need this, okay, if rational. So first, let's see the case where your voice or my speech signal is sampled at 4 kilohertz. Is it? No. 4 kilohertz voice is sampled at 12 kilohertz. So in this frequency domain, something like this. By the way, the most of the common conversation occurs here. So long ago, the public telephone network had a filter that cuts the signal at around 3K. So what happens? Your consonant 자음 with high frequency is a little bit suppressed or cut out. So it was very difficult to understand. And this was not the only problem of public telephone network, but also that happened in the communication between the control tower of the airport to airplanes, and even the command center of Air Force and fighter jets. So what happened? They kind of devised encoding methods. So probably you remember from some movie saying that the pilot communicates with the controller, says that the passcode is zebra tango blah blah, right? What they do that? They do not just say ZTH, something like that. They say zebra tango something. Why? They put redundancy so that even though my Z and C may be confusing, but from zebra, then they know, okay, they pronounce Z, not C, something like that. Got it? So some of you are going to do communications where we do compression and then systematic insertion of redundancy to have error protection. Actually, that is manually have been done in the communication between the controller in the control tower of the airport and the pilots of the airplane. Anyway, so this highest frequency content is around 4 kilohertz, and we have 12 kilohertz sampling rate, which satisfies Nyquist condition. So we are happy. And after we sample. So this is the 12 kilohertz sampled signal. But what's going on? So 2 pi is related to the continuous time signals 12 kilohertz. So pi is related to the 6 kilohertz. And you see here, this part is wasted. So for example, what you want to do is that to remove that one. Or sometimes you want to convert the signal and mix with some music played by a professional player. But usually musical instruments has frequency range much higher. So they usually sample at the CD quality sampling rate, which is 44.1 kilohertz. You remember that? This is very important. CD quality sampling rate is 44.1 kilohertz. And you need to do some, for example, some upsampling. Of course, in this case, this is not exactly 44.1, and sometimes that's happening. Got it? By the way, in audio signal processing or musicians, mixing means addition, actually, of two signals, summation of two signals, two or more signals. But in radio frequency engineers, mixer means multiplier or multiplying an RF signal with an RF carrier or something. So be careful. Electrical engineers usually understand mixing as multiplication, but musicians and composers, they understand it as summation. Anyway, in this example, 8 times upsampling, or upsampling by 8 occurred. And first, what happens? So this is what? You insert 7 zeros, right? Then what happens? It's the number of samples expand, which means that, or the samples period is expanded in the time domain. So it is compressed in the frequency domain. So you have now this one, pi is there. And if L is 8, you have 8 copies. And you don't want to have these signals. So sometimes you may have low pass filter that cuts out the signal. And here, instead of having this one with very sharp pi over 8 cutoff, you may implement this one in this way. So you upsample by a factor of 2 and low pass filter, upsample by a factor of 2, low pass filter, and do 3 times, and you have the same thing. And you may say that, why do we do that? Mathematically the same. As I told you, sometimes mathematically same procedure gives you tremendously different real-world implementation. And if you have taken my signal gen systems, the last part has some slides related to CD playback, where this multi-rate signal processing is really applied. So if you have a CD player, usually these days nobody has CD players. But anyway, what happens is that it is kind of recorded at 44.1 kilohertz. And what they do is that they first upsample and filter, and they interpolate with very fast D2A converter. Anyway, we can't hear that high frequency signal. Anyway, so there are many multi-stage or filter bank representations in this course. And here we have multi-stage, first, second, third stage, third stages that is equivalent to this single stage filter. By the way, usually it's not easy to have a very sharp filter. So with very low frequency, so we have something like this. Okay. The cutoff at around pi over 2 is rather easy to implement compared to the that one with pi over 8. Okay, and this part with a lot of figures, you read it. It's not that difficult. Okay. By the way, even though the this low pass filter, high pass filter, or band pass filters are in terms of the frequency, which means that we'd better have focus on their DT/FT. But the problem of DT/FT is that it's kind of low dimensionality. We want to think in a higher dimension. 고차원에서 생각하고 싶죠. So simple way is to just replace DT/FT with its Z transform. By the way, is it okay? It's okay, first, because substituting Z equals e to the j omega, you always have your original DT/FT back as far as your reason of convergence includes the unit circle. Here goes the second one. When we implement, we do not just use an arbitrary component to implement a discrete time signal, a discrete time filter. We usually use adder, scalar multiplier, and delay components. And this use of these components really motivates us to rely on the rational form of h of z. So a rational function of z. As I told you, it's not always the z transform of a dt signal is not always a rational function of z, but in order to implement it, we'd better approximate it to a polynomial, a rational function. In that case, we can use alternative representation of the system by using LCC DE, linear constant coefficient difference equation, which directly gives us how to implement the system using delay, adder, and scalar multiplier. And with downsampler, we may have some notation like this. And you may wonder, what's going on? But if you replace z with e to the j omega, then you remember, hey, I remember that. Before downsampler, if we have a interpolation, the pre-filter, then pre-filter had what? So let me go back to where it is. Frequency domain thing, where? Just a second, where is the interpolation? Okay, downsampling. Yeah, I cannot find where it is. Okay, where it is? Cannot find. Okay, anyway, you find it. One good thing as a professor is always I cannot find something, I just defer to students. So in multi-rate signal processing, you will see something like this repeatedly. Sometimes it's square root, but anyway. So you find why we have this Z to the M there. Got it? So let's see. Now, instead of using DTFT, we are using Z transform. But you can just understand it as what? Okay, here is an LTI system with impulse response called lowercase h sub L of N. Got it? It's not that difficult. So you have a pre-filter and downsampler, and you have a filter with another downsampler. Got it? And here, as you've seen, these two are identical. You can show that. So what you do is that downsampler and filter can be written this way. So similarly here, you switched order of these two, but we raised the Z to the power of M sub 1. Got it? And then these two filters can be combined, and these two downsamplers combined, and you have a single one. Similarly, for upsampling, you also have what? Here, you change the order of these two, but here, again, you have the power raised to the L2, and you combine these two and combine that two, and this strange multi-stage representation can be easily understood. Got it? So here, you switch the order of these two to have a single upsampler and filter, and then that filter and this one switched, and you eventually have single upsampler and a single filter. Got it? And as I told you, you need to spend a lot of your sharp pencils that lead. Okay. Anyway, so this multi-rate signal processing using multi-rate filter banks are used in speech signals. Kind of is old one. As I told you, the textbook is rather old, so it does not talk about MP3 players. But anyway, our old CD players had to have the discrete time filters and systems, really motivated by this course. But the trend has been a little bit changed because of the fast evolution of embedded system. So sometimes we have a very small computer, and probably you know there is some compute stick or stick PC, something like that. So even you can just put this size looking USB type thing to your big monitor, and actually it has Wi-Fi transceiver and CPU and memory, something like that. So the world has changed. So the about half of the news story is not covered in our textbook. Our textbook kind of pushes us to what? To the use of Z transform and the use of LCCDE, so that your old graduates of 10 years ago to, for example, implement some system using really delay adder, multiplier, something like that. But these days, your new task would be something like this. You put very small size of MATLAB-like general purpose computing software and let that do all the computing without implementing with hardware, but you implement these algorithms in software, which is much easier. You don't need to even consider this multi-rate conversion with upsampler and downsampler. Just insert zeros and filters, something like that, as you do in your homework. So remember, this book has focus rather old. However, still it's very, very important. Got it? Anyway, what you are going to do in your programming using MATLAB or some Python, you will do the same thing. Got it? Anyway, so here goes a perfect reconstruction filter. Here you have downsampler and upsampler and adder. And I believe this example is rather beyond the scope of undergraduate DSP. So I'm not going to talk too much about it, but you remember that there are many applications of multi-rate signal processing. And even there are some graduate level courses entitled multi-rate signal processing. And they have textbook entitled multi-rate signal processing. And multi-rate signal processing is very important. By the way, let me emphasize. Another thing is that, as I just told you, that you are not kind of, the textbook does not cover half of the story, doing embedded system and just programming. Another one is that even though the textbook covers, I'm not covering. Which part? When the input signal and the signal handles we handle are modeled as random processes. So the graduate level DSP course usually has much more focus on dealing with random processes, not just deterministic signals. So there is half of the other story. Please remember that. Got it? Anyway, just take a look at the figures. And whenever you are asked, as far as you have plenty of time, then just do it line by line, and which is not that difficult. So let me skip all of these things. Got it? Okay, here goes the what is really related to that CD playback. So digital processing of analog signals. And just to think about this analog signal is a speech or acoustic or voice signal. And what do we do? This is what we do. So here is my voice converted to an electrical signal. So basically, I'm using my muscles and my muscles around the lung and muscles attached to my jaws and tongue to convert my airflow to a desired acoustic wave. And in order to record that one, the genius Thomas Edison did what? Converted it to what? To a vibration of a needle. And actually, he recorded probably you don't know, but the first recording thing looked like a can of this current soda or something, Coca-Cola or something. So if you see the old picture, then you will see here is some, what is that, stenograph? I do not exactly remember the name the Thomas Edison used, but anyway, there is a can-like things with Thomas Edison's picture wrapping around, and actually these cans actually have a recorded version of song and music or something like that. And when it is played, what did he do? Because this needle moves very slowly, so he kind of combined this moving needle vibration with electrical system. So he combined this thing with actually telephone receiver and loudspeaker, something like that. So he was a kind of genius in combining new things to have another new thing. Anyway, so here goes the electrical signal, which is converted by using a microphone from acoustic signal to an electrical signal in our case. And we have what? C2D converter. And in practice, we have analog to digital converter that has what? Continuous time signal in electrical signal. It has first uniform sampler, then what? Scala quantizer, already forgot, and binary encoder, and generating usually line-coded binary pulses. Got it? However, as I told you, we just ignore quantizer and binary encoder, but just assuming that the continuous time signal is converted to a discrete time signal, as here. Got it? So this is really a mathematical model of our real electrical system having A to D converter and D to A converters. Remember that. Because we are so familiar with this kind of modeling, sometimes I have found that when I communicate with non-electrical engineers, they just do not understand why I talk a lot about sequences. Because discrete time signal is a sequence. And my mathematician friend said, why you are interested in a sequence? Because we model a digital signal. Even though it's line-coded signal, we just forget about it and just in our brain handle discrete time signals. Got it? And of course, when you use embedded system with some general purpose computing software like MATLAB, then you usually have the in your brain that you have a sequence. Anyway, here goes the DT system. And this DT system performs our desired action on this signal. And then eventually it could be recorded somewhere and retrieved later and converted back to a continuous time signal. That is actually CD player. Of course, when they store, they do not just store it. Sometimes they compress, they do source coding, and then they do channel coding, and then store. Sometimes source coding is ignored, so only channel coding is done. So, for example, if you have a CD or DVD disk, what happens? That does not contain the raw data. Actually, it's error control coded one. So that you have, for example, put your CD or DVD and just push them to have a surface scratch. As far as your scratch is not too deep and wide, usually there is no error when you play back. What I have found from our postdoc library is that usually these days we just subscribe Netflix or Disney Plus so that nobody goes to our library to borrow Disney's some movie like Cinderella or something. But I had I had visited, and sometimes I put it in my PC. The CD DVD player cannot recognize, so I took the disc back and watched the surface, and there was too much scratch. Why? This is my just guess. So a student or professor borrows a DVD disc from the library and put somewhere in at home, and the baby or children just plays it with sharp surface and a lot of scratches so that our error control code cannot handle any longer, something like that. Anyway, so it's very good to have our Disney Plus and Netflix these days. Yeah. Anyway, so this is the digital processing of analog signal example. Got it? Of course, here we have we don't have infinite precision and we don't have ideal low-pass filter, but they are kind of foundations of our real-world implementation. And here goes a more practical diagram. So this C to D converter is converted to 3 systems. And actually, these 3 things are all in the A to D converter. And by using some deep switch type input to your A to D converter, anti-aliasing filter can be selected, and its cutoff can be selected, something like that. Anyway, this is a kind of practical implementation, but not always. This is a kind of example. Got it? And here, sample and hold is an intermediate procedure to have an analog signal to an analog but discrete level signal. Got it? And we have A to D converter, which really converts an analog sample to a finite length of bits. Anyway, by the way, here we have so-called anti-aliasing filter before sampler, because this is kind of sampler followed by a rectangular shaped impulse response filter. And this anti-aliasing filter sometimes just abbreviated to AAF, not Air Force, anti-aliasing filter or anti-alias filter. And this is to, as the name says, remove aliasing. So from the sampling rate, it recomputes its cutoff frequency and then cuts out all high frequency components than the half of the sampling rate, approximately. Got it? So remember this term AAF. And here goes what you need to remember. Our ear can hear up to 20 kilohertz. That's why, as I told you, the CD playback system has sampling rate 44.1 kilohertz. By the way, you may say that, why 4.1 added? Because at that time, we had to have practical filter with little bit slow rough. So we had the margin around this one. Got it? Anyway, this is what we can generate. Our speech system can generate, but for usual daily conversation, not you play a song, around 3 kilohertz is enough. Got it? Anyway, so for voice only, you may have lower cutoff frequency for your anti-aliasing filter and lower sampling rate. And that really happened long ago for our telephone system. But from 4G LTE, our cell phone, it has much better codec that allows high frequency sampling. So probably you have in your LTE system long ago, you have sometimes turned on your voice over LTE, then the quality was very good. But unfortunately, even at that time, if you call to your friend who are subscriber of different cellular service provider, then the quality was suddenly dropped because usually at that time, it was not kind of all IP based. It was converted back to a low rate signal and then converted back to high frequency. So that happened. Now it's not like that. Almost everything is IP based. So your high quality voice signal is kind of transferred to almost everybody. But however, still some of the old telephone system, if you have real 집전화, not IP phone, you may suffer from this lower cutoff frequency in your system. Anyway, so if you want, you may just say, okay, let me take this anti-aliasing filter out and then see to the converter that just evaluates this one at every capital T. Got it? And you have the discrete time processing of continuous time signal. Ideal case, your anti-aliasing filter may have ideal low pass or band pass property. In this case, low pass property. In practical case, you may not have ideal filter. You may have some filter in the frequency domain that does not have very sharp roll from this pass band to stop band. in that case, what happened? What you do is that you use this highest frequency so that you have, again, still no anti-aliasing or no aliasing or very small aliasing. And then you convert. But after you sample, digital processing usually can be done much accurately with a lower cost. So they do sharp cutting off and then downsample. This is what I told you. So usually we think, okay, let's do ideal sampling, low rate, or for example, 44.1 kilohertz sampling with very sharp anti-aliasing filter. That's not happening. They have a little bit slowly roll-offing filter, but with twice or 4 times higher frequency density quality sampling. And after they have higher sampler, high rate sampler, in digital domain, discrete time domain, they do ideal filtering or approximate ideal filtering and then downsample. Then this is very close to this case. Got it? So in the frequency domain, this is what's going on, and you can easily understand. So here goes the practical filter that may contain some bad singing. We cannot hear, okay? So as I told you, suppose this is our hearable, okay, or audible range and bats singing signal, okay? So we sample very fast. So we have this kind of signal after multiplying sampling function. And then in the discrete time domain, we filter this part out, having this almost ideal low-pass filter. And then we downsample. What happens? These things, each one expands like this. Got it? Then the resulting signal is like we have originally very sharp cutoff anti-aliasing filter and low rate sampling. Got it? So as I repeatedly told you, something equivalent can be very, very effective in practice. And you may say that why we do m times faster sampling and downsample by m? Because in this case, we cannot implement almost ideal low-pass filter in the analog domain. So we upsample, so we have a little bit room to maneuver. And in the discrete time domain, we have very ideal, like sharp cutoff filter, and then we downsample to achieve our goal. Got it? Okay. Here was the story about the sample and hold. I really hate because I have no idea about how they really implement this as a circuit. But sample and hold can be understood this way. So you have an analog circuit, and here you have a sample and hold output. By the way, sometimes it is abbreviated as SOH. Is it right? No, not SOH, S/H. So you may see some textbook or diagrams saying S/H, sample and hold. And of course, it has parameter capital T. What happens? As I told you, if we arbitrarily choose offset 0, then at every T, we sample and hold, sample and hold, sample and hold. That is the ideal sample and hold circuit or system. Of course, the circuit guys tries to approximate this one. I don't know how, but anyway. And then what does this do? Here again goes the clock input, and usually they are synchronized with some offset. They take the middle value so that no transition occurs. So at this middle, they have scala, some voltage or current. Then they have mapping rule that assigns a finite number of bits from all zeros to all ones, depending on how they assign the A to the conversion function. Of course, the simplest one would be this one. Something like Gauss function-like thing. You really hate it in your high school math problems. I agree. It's like when I was a high school student, not many problems had this symbol because we had a lot of other important questions to ask to students. But as you know, around half of the high school math curriculum is gone during last 30 years. So what happened? Students study much harder than I was a student. And the coverage is reduced into half. So those committee members of the aptitude test, 수능, especially math, they devise strange problems involving a lot of Gauss functions or floating or ceiling or rounding. I really hate. Anyway, unfortunately, even that part occurs in electrical engineering. So as I once told you, almost every part of your high school math appears somewhere in our course of electrical engineering curriculum. But be careful here. This looks simple. And you may say that, okay, so here we have, so this function may employ rounding function, right? So we may have three functions, right? So let me ask you, what about this function? What's the graph of round of x when x is real? As you know, up to 0.5, you have 0, right? And from 0.5, you have 1. 1.5, you still have 1. So if you have continuous kind of same idea, then you must define this way, right? So it's not that difficult. What about ceil of S? What is the ceiling? If you have 0, then it's 0, but greater than 0, then suddenly it becomes 1. So this is 0. And what about 1? It's still 1, but suddenly it becomes 2. Then you have something like this. What about floor of x, flooring? Then if you have 0, it's 0. If you have up to 1, it's 0. And you have jump, blah, blah, blah. Got it? And here, this example shows the case where it employs something similar to round of x. Of course, here, not round. This is, if I remember correctly, round x over delta.
Dr. Joe, it is time to wrap up. Dr. Joe, it is time to...
Times delta. Got it? So the first part is done. And what about this one? So SUMAT is not kind of expands to infinity. Why? Because we want to assign a finite number of bits to different levels. And here goes something very important, which is often disregarded by many people. See that here? So you have 5 delta over 2. Something's different, right? Here you have flattened the region here, but there actually. Why do we have that? Because usually, how many levels do we have? When we assign bits, even numbers. But if we use round, what happens? We never have symmetry, right? If we have ceil and floor, we may have some symmetry, right? Because from 0, we have something, and exactly the same thing occurs here. But if we have round, we have something strange. So in the future, not many of you, at least one of you, suddenly find something is not symmetrical in practical A to D converter. Because usually, not always, usually they have what? They have some small number assigned to 0. So they can never have symmetry because we have even number of levels, but we have this part centered there. Right? Anyway, this was really confusing. Frankly speaking, I realized that one around 3 years ago when I was 52 years old. Can you believe that? Even though I always said that, hey, here is a quantizer and did assignments. Yeah. So anyway, you know that. So you are much better than me. Okay, anyway, let me stop here for today. And the coverage is very slow. And as I told you, the core of this course is DFT. Well prepared. Got it? Okay, that's all for today.